Hello, thanks for coming to my presentation. This is Yuzhe from the University of Wisconsin-Madison. This talk will be about sequential attacks on common filter-based forward collision warning systems, and this is a joint work with John, Ruizhe, Earlence, and Jerry. To get started, I will give you some background on the forward collision warning, or in short, the FCW system. The FCW system is a popular driver assistance system that has been widely used in cars today, and it's designed to monitor the scene in front of the car during driving and produce warning alerts to human drivers in case of danger. While FCW is a traditional control system, it also has integrated a lot of recent machine learning techniques such as object detection and tracking. However, despite being a popular system, it's not fully understood what are some potential security issues in FCW. In this talk, we are going to take a step towards understanding the security property of FCW when attacker exists in the system. So first of all, I'm going to use the following example to explain how the FCW system produces warning alerts to human drivers in different scenarios. In particular, this talk assumes an FCW system that generates warning lights red, yellow, or green, depending on the state of the car in front of us. From now on, I'm going to call the left car the victim car, because this is a car running FCW, and we are going to consider how to attack its FCW system in later discussions. I'm going to call the car on the right the leading car. The relative distance and velocity of the leading car with respect to the victim car are represented by dt and vt. Here the distance dt is always positive, while a positive velocity vt means that the leading car has a higher absolute velocity than the victim car, therefore is moving away. We use the right arrow on top of the leading car to denote this situation. In order to facilitate FCW, the victim car needs to equip sensors to measure the distance and velocity of the leading car. In this talk, we assume the victim car adopts a camera sensor and a radar sensor, both trying to measure the same distance and velocity. The core component of FCW is a Kalman filter, which takes in the measurements from both sensors and performs sensor fusion to produce a state estimation for the leading car. This is like a syncing process, as shown in the syncing bubble above the victim car. The dt hat and vt hat here are the estimated distance and velocity, which ideally should be the same as the ground truth value, but in general, there's always going to be noise introduced from sensor measurements. So the Kalman filter state estimation in the syncing bubble is only close to the ground truth value, but can never achieve that. I would like to mention another important aspect about Kalman filter, which is sort of characterized by the loop between the syncing bubble and the Kalman filter rectangle in this plot. This loop of double arrow means that the Kalman filter is a sequential system, and it performs state estimation by smoothing the state estimation in the previous time step, which is t-1 here, and the current measurement at time t. This also implies the state estimation we obtained so far intrinsically depend on all historical measurements. And we will revisit this when we talk about the attacks. Given the state estimation at time t, the FCW will take that estimation and produce a warning light. Specifically, we can view the FCW warning alert logic as a function of the current state estimation, dt hat and vt hat. Different dt hat and vt hat will lead to different warning lights. Geometrically, if we consider the 2D space formed by d hat and v hat, then the FCW warning alert logic is going to form a partition of the 2D space into 3 regions, as shown in the panel above the syncing bubble. Each region here corresponds to the set of all possible state estimations leading to that warning light. In this first scenario, the leading car is moving away, and there is no potential danger. Thus, we see that the point corresponding to the current state estimation lies inside the green region, and the FCW produces green light. So next, let's take a look at the second scenario, where the leading car has a negative relative velocity, meaning it's actually approaching the victim car. Then the Kalman filter will produce a state estimation that leads to a different point in the 2D space. And in this case, it lies in the yellow region, and the FCW produces yellow warning. But before I move on, I would like to mention that the FCW alert logic and the 2D space light partition we used in this talk is exactly the same as in standard MATLAB FCW implementation. So this leading car is approaching the victim car, and after a while, we would expect the leading car to be very close to the victim car. And this is our third scenario, where as the distance shrinks, the Kalman filter state estimation gradually moves downward and crosses the boundary between the yellow region and the red region, which causes the FCW to output a red warning. This is when the situation becomes very dangerous and the human driver must take a brake action to avoid collision. Now that we have introduced the normal process of an FCW system, next we are going to discuss how such FCW system could be adversarially manipulated by an attacker. There are different possible attack goals one can consider in practice. In this talk, we will focus on a particular one where the attacker hopes to change the warning lights produced by FCW. This attack goal is of primary interest to us because it targets directly compromising the functionality of FCW, in the sense that under certain scenarios, causing FCW to output a wrong warning light will be extremely dangerous. For example, let's continue our discussion on the red warning scenario, where the leading car is already close to the victim car. In this case, an attacker might aim at changing the warning light from red to green. This corresponds to move the state estimation in the 2D space from the original red region into the green region, or in other words, make the velocity estimation greater than 0. For example, one can consider move the original dot to the location of star symbol in the green region. As a result, if the human driver of the victim car is not paying attention to driving, such as on phone or in chat, then this attack is going to be devastating and will lead to car collisions. But the question is, how realistic can this attack be in practice? To answer this question, we first need to define our attack surface on the FCW system. And this is going to involve both the sensors and the Kalman filter. In particular, in this talk, we assume the attacker has the ability to manipulate the measurement recorded by camera. We make this assumption because nowadays there has been plenty of papers on adversary examples where the attacker can perturb the pixels in the image to cause a different output. This matches what happened for the camera. Specifically in FCW, the measurements from the camera are usually obtained by first taking an image of the scene in front of the victim car, and then applies neural network-based object detection algorithms on the image. This is where our attacker can perturb the camera image and causes different measurements output. However, we point out that in our paper, we do not consider image-level attack, and our focus is to develop sequential attack methodology, and we will leave image-level attacks to future work. So from now on, I'm going to assume the attacker can directly hijack the camera and manipulate the measurements there. Then the question is, how does the attacker manipulate the camera measurements to change the red light to green light in this case? As you might have observed, the velocity estimation produced by Kalman filter is around -10. So the first option here is to simply increase the velocity measurement from camera by 10. However, this is not going to work because we still have radar measurements that are not subject to attack. If the Kalman filter takes the average of the camera and the radar to estimate, then this attack only increases the velocity estimation by 5, which moves the original dot to the star in the yellow region, which produces yellow light instead of green light. So immediately the next option is to double the increase to 20. However, this is still not going to work in most cases because, as we said before, the way that Kalman filter performs estimation is by smoothing the state estimation in the previous time step and the current measurements. Therefore, the previous state estimation can sort of cancel our attack effect here. That means if the attacker increases the velocity by 20, the Kalman filter velocity estimation might only increase by less than 10, which still cannot lead to the target green light. So these two attacks share the same spirit in that both are instantaneous attacks, where only the current measurements are manipulated. This typically requires a large attack cost, meaning the attacker needs to significantly change the measurements in order to cause the desired warning light. In contrast to instantaneous attack, we know that the Kalman filter performs sequential update of state estimation. This means the historical measurements starting from the very beginning until the current time step or influence the state estimation so far. Therefore, it's quite natural to consider manipulating the whole sequence of measurements continuously over time with the hope that the manipulations can cumulatively drive the current state into the target light region. This is what we call the sequential or continuous attack. On the left plot, I illustrate the desired state estimation trajectory in the 2D light space under continuous attack, which finally enters the green region. So now we have briefly described the idea behind the sequential or continuous attack. Next, I will spend some time talking about why do we prefer sequential attack. There are mainly 3 reasons for that. First, the sequential attack is more likely to be feasible as compared to instantaneous attack. This is because in practice, there are often physical limitations in terms of how the attacker can change the measurements. For example, the relative distance must be positive, and there might also be an upper bound on the distance where sensors cannot work out of that distance, such as 80 meters. The relative velocity must also be within a reasonable range, for example, between -20 meters per second to 20 meters per second. The ranges here are just for example and can vary depending on the FCW implementation. Instantaneous attack could require very large change to measurements that break those limitations. In contrast, the continuous attack or sequential attack spread the manipulations more evenly over the entire attack horizon. Thus, each step could require a smaller change to measurements. Therefore, sequential attack is more feasible. Second, the sequential attack is also more effective because it can exploit the sequential nature of FCW system by accumulating the attack effects over time. And finally, the sequential attack is more stealthy because it can spread the manipulations more evenly over the entire attack horizon, where the manipulation in each step becomes relatively small as compared to instantaneous attack. Therefore, the sequential attack is less likely to be detected and more stealthy. So next, I will show our formulation of sequential attack. In particular, the objective function equation 1 here represents the cumulative norm of the manipulation over time. This can be viewed as the attack cost. Then equation 2 is the attack action, where an additive manipulation term delta t is introduced to the clean measurements yt. Equation 3 here still simulates the Kalman field state update, while equation 4 dictates that the attacker only manipulates the camera component in the measurement yt. So similar to the epsilon norm ball constraint in standard adversary example papers, we also have equation 5 that restricts the attacker's manipulation on measurements to be bounded. And also, as mentioned before, equation 6 is the natural physical constraints on distance and velocity. The attack goal is characterized by equation 7, where capital T dagger is a target interval, and for each time step in the target interval, the attacker hopes to force the FCW system to output a desired warning light LT dagger. Finally, in our paper, we enforce the attacker to be as stealthy as possible, which is characterized by equation 8. Here, the T superscript S is what we call stealthy interval, and this is essentially the time steps where the attacker can manipulate the measurements, but does not have any desired target warning lights to force. Therefore, in this case, we require the attacker to not change the warning lights compared to without attack. Here, LT is original light produced by FCW when no attack happens. Unfortunately, this attack optimization is not well defined because equation 2 involves future measurements that cannot be observed. To tackle this difficulty, we propose using model predictive control, or in short MPC, to plan the optimal sequence of manipulations. Here's a diagram of our MPC-based attack framework. The whole procedure starts from step 1, and in every time step, the attacker first predicts future measurements based on some assumed generative model of the measurements, and then plug those predictions into the previous attack optimization formulation to replace those unknown future measurements. This allows the attacker to directly solve the optimization and obtain a sequence of manipulations from the current time step little t to the target time step capital T. Then the attacker carries out only the manipulation planned for the current time step, which is delta little t, and discard the remaining ones. Afterwards, the system proceeds to the next time step, and the attacker enters the next MPC iteration and replans a new sequence of manipulations, and so on and so forth. So in summary, by using model predictive control, we are able to plan the attack over time. So in the rest of the talk, I will show you some empirical results of our attack. First, I will introduce our experimental setup. In our paper, we use Color, an autonomous vehicle simulator, to create an environment similar to the real-world driving scenario. The simulator allows us to set different initial conditions for the relative distance and velocity for the leading car. In particular, we created 2 test scenarios based on standard testing protocols for FCW. The first scenario is what we call the MIO -10. In this case, the victim car is driving in the same direction as the leading car. The velocity of the victim car is 27 meters per second, which is approximately 60 miles per hour. This represents a standard velocity in real world. The leading car has velocity 17 meters per second, which is 38 miles per hour. So the victim car is gradually approaching the leading car in 10 meters per second. The original warning lights without attack is shown in below, where in a long period after beginning, the warning light keeps yellow, and then at step 100, the 2 cars get too close, and the FCW produces red warning. In the absence of an attack, the FCW alerts in time for human to react and brake to avoid collision. And the attacker's goal here is to change the warning lights from red to green in the target interval, where the target interval is after step 100 and corresponds to the red region. Here's what happened after attack. As you can see, The warning lights in the targeting interval are changed to green. Therefore, the attack is successful and will lead to car collisions. Furthermore, note that even if the attack starts early from step 1, it does not change the warning lights before the targeting interval. That means our sequential attack is stealthy. Now let's take a look at the measurements. Let's take a look at how measurements are changed. The left plot is for manipulation on distance, while the right plot is for manipulation on velocity. It's interesting to see that the attacker chooses to not change the distance a lot, but increases the velocity of the leading car to be positive. As a result, the victim car believes that the leading car is moving away, thus the FZW produces green light. Our second scenario is called MIU plus 1. There are 3 cars, the victim car, the leading car, and a trailing car. In this case, the leading car is faster than the victim car, and it's moving away slowly with relative velocity 1 meters per second. The trailing car is behind the victim car and has the same velocity as the victim car. Without attack, there will be no danger, and the FZW produces green light consistently. The attacker's goal in this scenario is to fake red warning alerts during the target interval so that the victim car believes there is an imminent danger and output red warning. The human driver of the victim car may choose to brake suddenly, and if the driver of the trailing car is not paying attention to driving, then there could be a real collision happening between the victim car and the trailing car. Here the result of the attack. Again, the lights in the target interval are changed to red, but there are some minor side effects of attack between step 40 and step 80, where the original green lights are changed to yellow. Looking at the manipulations on distance and velocity, the overall trend is that the attacker decreases the distance and velocity to make the victim car believe that the leading car is being close and also approaching fast. Therefore, the red warning is produced. Finally, we simulated our sequential attack in color, and here are some videos. So the left one is for MIO minus 10. And our attack causes a collision. The right video is for MIO plus 1, where the red car is the trailing car. And after our attack, the trailing car bumps into the victim car. So to see the full simulation results, please check out our website. Finally, to summarize, we propose a planning-based sequential attack framework, where planning means the adversary can plan its moves ahead of the target time step. We also provide a demonstration with a realistic autonomous vehicle simulator, and we show that our attack can cause car collisions. And that's all for my presentation. Thank you for listening.